yesterday there was something like this, n c j times n. This was dividing ln, right? So j times n. Right, thank you. It was j times s, and this was dividing this verticity LCM of 1 to n, right? And this was for all j in the range 1 up to n. And then we say that implies what we do here, we put j plus 1 or something. No, n plus
that should be like n plus 1 into n choose j minus
1. N plus 1
into.
I mean, you know this for n plus 1 case, and
yes,
then
so we replace n plus 1.
So
this divides
LL
plus 1. And then we rewrite this.
Yes.
So we say that 3 times n plus 1
Choose
j. This is equal to
n plus 1. Yeah, now n plus 1.
I was just writing down the factorials.
Oh.
N plus 1 factorial by n minus j plus 1 factorial by j factorial. That is, we can take this one out, n plus 1, and upstairs we wrote n factorial by here j minus 1 factorial times n minus j minus 1 factorial. That is n plus 1 times nc j minus 1. Okay? Okay. So this was this. Wait, by the way, note that here j was running from, well, this was true for all j from 1 to n plus 1, right? So now the thing was that we assumed now that if we take some j which is co-prime to n plus 1, can we write, so if density of j and n plus 1 is equal to 1, does that imply that n plus 1 times this divides n plus 1. So that was the question. Right? And if we have that, then the rest of the proof is fine. So not that. Here it was n and j minus 1, and we had that this is dividing n minus 1. Right? So let's rewrite that for this one. So that was n plus 1 times n choose j minus 1. Right? For all j in this range. 1 to n plus 1. That means if you replace j with j plus 1, you have n j here. Okay. So, and note that j was in this range, so j plus 1 is indeed in this range.
Oh, and since j is co-prime with both of them, you don't need to worry about j.
Exactly. So that in particular implies. So wait a minute. This one was for this, and now replacing j with j plus 1, we have n plus 1 times n into j. This divides n plus 1 for all j in 1 to n. So this indeed implies this because we have now, if you replace j with j plus 1, you have that this is equal to, j minus 1 here, and then that implies that, well, what it implies we have written it already here, is n plus 1 times ncj, this divides ln plus 1. Now, if n plus 1 and j are co-prime to each other, and since you already know that j times ncj divides ln, and ln divides n plus 1, it follows that this one and this one both are dividing n plus 1, and n plus 1 and j are co-prime. So that would mean that n plus 1 times j times this one divides n plus 1. So this is the integral. So yesterday we saw Nayar's proof, and here we used this fact that, well, in Nayar's proof we obtained that ln is larger than or equal to 2 power n, and then we saw that ln is bounded above by n power pi n. Okay. So, and then you take to log. Now we are going to complete the proof of Chebyshev. It is the way we are proceeding with Chebyshev. We are not going to get as good a bounding parameter because here we obtain phi n, and finally we obtain that phi n is larger than or equal to n phi from 2n, that is log 2 times n by n. So this was the bound we obtained from Nayar's argument. And from Chebyshev we are going to get something like 3 log 2 by 8. That's from output. Chebyshev, well, Chebyshev himself proved it for, let's recall it. A approximately about 0.9213, and B approximately 1.1055. Now why this constant are it is, well, it just says means that pi x is approximately equal to x by log x. Now that's actually what I want to mean is that asymptotically equal pi x is so this equality means pi x is asymptotically equal to x by log x. Okay. Now the importance of these constants to be seen from at this time when she proved this, there was something in 1845 Bartrand stated this postulate, that is there always exists a prime between n and 2. So it's striking that. Shivshev's was announced in 50 and was published in and in 1845, but actually stated this for all n there always exists a prime p in and then for all n greater than or equal to. Because if you take n equal to 1, then it is 1 and 2, and you can say that it is equal to 2. But so Barton's postulate, if we write it in a numerical form, it will be so. This is just meaning that there is a prime p, and Barton went there is strictly written in that way. And if you can check, there's if n equal to 2, there's 4, there's 3. If you take n equal to 3, there's 6, so there will be 5, and so on. So now, how should you prove this? That if we have, so the number of primes which are less than 2n plus pi 2n, and the number of primes, well, if n is larger than 2, 2n is never prime. So pi 2n is the same as pi 2n minus 1. And then the number of primes less than n is pi n. Right? Now, if there is such a prime, that would mean that pi 2n minus pi n, this is greater than 0. Okay. Now, we should obtain this bounds, right? X by log x. So, for this one, the lower bound is then 2ax by log x. As for this one, the upper bound is bx by log x. So if this is greater than 0, that would imply that this happens. Right? So if a and b are such that this is happening, now let's write this. What type of A and B should suffice? Let's write them down. So Barton strength is postulated and verified it for all n. Barton, and remember, this is not Barton Russell, but it is Joseph Barton. Russell's paradox and Barton's postulate are not stated by the same Barton. It's the last name and that was the first name. So Barton verified it. For all n less than equal to 6 times n over 6. And then is this. And which was proved soon afterwards by Shivshev. So let's simplify this. X by log x. Wait a minute. Here we get 2x, right? So here we will log 2x instead. Sorry. X. Because we are using the lower bound for pi to x. And then the upper bound for pi x. Dx by log x. So let me there.
N.
Which one?
I mean, is it strictly between N and P2N, or could it be that P is the same as N?
This argument that we are giving.
No, the one like Barton is supposed to.
Oh, Barton first is strictly between n and 2, because and for all n larger than 2, this will happen. But if you take n equal to 1, then it will be equal to 12. But for all the n larger than that, this is not possible. And this argument what we are giving, actually the proof could be done in this manner if the a and b are good enough. And that will show that you can take p strictly larger than n. So this is what you take h1 log x outside, and then here you have 2a, well, x log x you are taking outside here. It will be 2a, and well, you have a log x factor here, minus b log 2x by log 2x. So that would mean if you replace this log x with log 2x, that is, if you just add to this one log 2 times 2a, then you can take the log 2x common and cross it out with log 2x there. So that would imply x by log x times 2a minus b minus 2a log 2 by log 2x. Note that this one goes to, this one becomes very small as it goes to infinity, whereas this one is, all you require is that 2a is just a little bit larger than some b plus epsilon. And note that this is already satisfied by the bounds that initial bounds that Chebyshev obtained, because 2 times this is like 1.8, and that is like larger than b by 0.7. So that will do that. Whereas the bounds we are going to get are not that. We are going to get, I mean, in our proof, we will take a is equal to p log 2 by 8, and b would be about 6 log 2. So you see, 2a would be 6 log 2 by 8, which is far smaller than b. So this, I mean, the bounds we would get will not establish Barton's possibility. Okay? But this can already be done a bit better. I mean, yesterday we saw that we would get log 2 here from 9th argument, and this one would also be made a bit better. Let me just so we prove this theorem arguing that the product of the times p say less than 12n is less than over n. Now note that implies the product of the times p less than 12n and say which are larger than some t, for t in the range, say 1 total n. This is less than, again, forward n, right? Okay. Now note that each of these primes are larger than t. T is is in some range between 1 to n, 1 to n enclosed. So that implies that t power, how many branches could be in this range? Pi n minus pi t, right? Pi t is less than 4 power n. Take it out on both sides. What does it give you? Pi n is less than n log 4, okay, plus, and you get pi t. Okay, wait a minute. There will be log t factors as well. So, pi n minus pi t times log t, that is less than n log 4. Simplifying. What do we have there? Pi n log t less than n log 4 by log t. So, and there will be pi t log t on this side. Note that pi t is less than or equal to t, right? So we get there plus t log t, for all t in this range 1 to n. So what do we do now? Sorry, there will not be log t factor anymore because we divided with log t. So how would you proceed? Now your task is to minimize with respect to
It
t.
should not be t log.
T.
It should just be t.
It would be
Just
t. Thank you. Yes. Yeah. Oh. Yeah, because we already divided that. Thanks a lot. So now your task is to minimize it with respect to t. So there are two tasks. One is that minimize the right hand side with respect to n. I mean, you can take t in this range, keep n fixed, and see what is the minimum value that this can have. And two, check that for t equal to n by this is very less n by log n log squared the right hand side would be like log 4 plus epsilon. It will be very close to log 4. The RHS is of the form log 4 plus some epsilon n, the epsilon is very small, times n by log n. is our true log 2, and here from ninth argument we got that the lower bound is the coefficient could be taken as log 2. Okay, but there, I mean, for this to be true, we require a to be, I mean, a to be like 2 times a would be like e plus epsilon. Epsilon is quite small, and epsilon is as small as you wish, because this is going to infinity. This is going to 0 as x is going to infinity. But this one is worse actually, because this is we actually require log 4 minus epsilon, and this is just a bit larger than log 4. So this is not quite satisfying this one. So for proving Varda's postulate, along with this observation, you will also use something. Let's write it down somewhere. So which one? I think you will still lost. What I'm saying is that here we require, to prove Varda's postulate in this manner, we require that 2a is larger than 2 plus epsilon. Whereas this one is giving us, we saw that here from that argument we can take b as log 2, and from this one we get equal to 2 log 2 plus some epsilon. So what we required, wait a minute. B was the upper bound, excuse me. So from the next argument we got A is equal to log 2, and B we required B, so I mean A and B such that 2A is larger than 2 plus epsilon. Whereas here we are getting this is 2A is just a little bit less than B. So that's why this one directly doesn't help, but we use another lemma with this. Yeah, so indeed we need some more constraint on the range of the primes we are allowing, and that was about this lemma, which will be useful later. Or we can prove it. It's very simple actually. So what it is? Let B a prime so that 2n by 3 is less than equal to b less than 3. For n larger than 3, then p doesn't divide 2n to 7. So here we go. Well, if p is in this range, note that 3p is larger than or equal to 12. Right? So how many multiples of p are less than 12? P and 2p. But p and 2p, because 2p is still less than 12, right? But 3p is larger. Only multiples of p larger than not smaller than 20 are p and 2p.
I think I see, because n is appearing at the bottom twice.
Exactly.
So you are basically counting out the two possible multiples.
Right. So what is the highest power of p that dividing the denominator of the LCM is p square. Right. And what is the numerator? It's again p squared. So they get cancelled. Right. That's all. So that implies p square is this have you seen the sign? This means exactly divides. That is the highest power of it. Hence, Qn now. So Qn factorial by n factorial squared. So p squared is exactly dividing this because p is appearing only twice below. I mean, the multiples of p is only appearing twice among the integers less than 2n. And in this one, p is only appearing once. Sorry, in n factorial, p is only appearing once. The square root is appearing twice. So they get cancelled. That implies that p doesn't divide this. So we are going to use this along with this one to obtain butterfly speed. But before going here, let's first complete the proof of solution and then proceed. So, which solution? What was the status? How far did you proceed? Let's recall what we have done so far. We are considering the divisors of 2n choose n, right? The prime number of 2n choose n. And we saw that 2 power 2n by 2n plus 1, that is the average value of average of the binomial coefficients of 1 plus 1 over 2n is less than the highest one, is 2n choose n. And then this one is the product of the primes that divides the product of the primes less than 2n and power. So since you write it in factorial notation, you get this one. So this is just p power vp when factorial minus vp in factorial squared. Okay. And that was
Here the other method that would be this.
right.
He also considered from this, like the binomial coefficient and then average of the coefficients.
Right. So this was the average of the coefficients. Yes, and this is smaller than the largest one. Okay. Right. This. This one was equal to the product of the primes is 2 p, and here you get sum 2n by pk fluid, sum of k. Just 1 minute, we need a little more space. Write the upper limit of the sum. So this is product over p is an n p power sum k running from 1 to log 2n is p, and here we had 2n by e power k floor minus 2 times n by k. Right? And each of those were 1 or 0. So this is less than or equal to product b less than 2n e power log b 2n. And that is, well, each of these is 2n. And how many are here? The number of primes that is n to 2n. This is less than equal to 2n whole power pi 2n. So this was the thing. And also we had that this is larger than 2n for all n, but for all n larger than 3, right? This is also something. Yeah, any doubts? So this was our argument so far. Obtaining the this is still about obtaining the lower bound.
We need it last.
Yeah, we need last one. Now you will take logs on both sides. So n then log 2 is less than equal to pi 2n log 2n. So yeah, right. So that implies pi 2n is larger than or equal to log 2 by 2 times 2n log 2. Now, one thing.
Pi 2n.
Yes.
Pi 2n equal to pi 2n minus 1.
Pi 2n is of course equal to pi 2n minus 1 because we are taking it at larger than 3. But now, if you choose in that well at first, yeah, let it greater than 3 or now we would like to get such a result for arbitrary x. Right? So let x greater than or equal to 8 be such that 2n less than or equal to x less than n plus 2. And well, we are assuming that n is larger than or equal to 3, so it's fine. Well, no, here it will be equality, and here on the left hand side, you have strictly better because we are assuming x is larger than or equal to 8, so the minimum value of x is 8, whereas the minimum value for n here assuming is 3, so 2n is 6, and then there should be equal to the right hand side. Also note that this function x by log x is increasing for x less than x less than e. How do you show that? Note the sign of the derivative and check that it's negative in this range. Now, let's say that this is 3x by 4. This is required, this is less than 2n. Is that true? 3x by 4 between 2n and what is it? So what we are, how are we going to proceed? We would have pi x here. This is larger than or equal to pi. And then we have that this is greater than or equal to log 2 by 2 when by log 2n. So if we get some constant variable of x which is bounded above by 2n, we will be done, right? That we can put there and get the corresponding constant here. Okay. So let's check this one. So that would mean 3x is that is equal to 3x is less than 2 n minus 2 that would mean 3x is less than equal to 8n, right? And what we have here, x is less than equal to 2n plus 2, so 3x will be less than equal to, this will imply that 3x is less than equal to 6n plus 2, and all we require is that 6n plus 2 is less than 8n, which is true in this case. Yeah? 6n plus 6. This is plus 6 right here. So this implies that x is less than equal to 6n plus 6. So 6n plus 6 is less than equal to 8n for all n larger than equal to 3. Right? No, we don't have to think so much because you see for 3 it goes. And then it is this one is larger than this one. So now what we do most place here is on the right hand side of this one. It is you have like this is larger than log 2 by 2, and here we would just we still need something that is 3x by 4 needs to be larger than e, and x is larger than equal to 6. So that means 3x by 4 is 6, right? I mean, 3x is minimum value for 3x by 4 is 6, which is larger than e. So we can still write that this is larger than 3x by 4 times 2. No, sorry. We are using it instead of. So we have 2n larger than equal to 3x by 4. Yes, and this is larger than e for the given range that is x greater than equal to 8. And so this is 3x by 4 by log 3x by 4. And now simplify this. Well, this you can just take 3 log 3 by 4. From there you can just take that into the constant. Whereas here we have x by this one, log 3x by 4. But log x is larger than this. So if you replace this by log x, that would be smaller than this one. Right? So you can write this is greater than log x. So this is giving you a lower bound for pi x. Well, a lower bound which is worse than the lower bound we saw yesterday from Nash group. But nonetheless, it's for all x in this range, well, all x larger than equal to 8. And then what you do from 2 to 8, you verify it numerically. You know how the function grows, in which range it is decreasing, in which range it is increasing. Use that fact, allow with numerical verification at the intervals.
So yeah, these guys are very important.
This one?
Yeah.
Okay, thanks. So, verify numerically. For x in the range. Now to prove the lower bound. P in this range n to n is divided this one. Because if you expand this, you can get that upstairs, below you get it squared. And so this branch do not appear in the equation. And then this implied that since each of these prime factors are larger than n, that implies that n power 5 to n minus 5n, this is less than with just n, and which is less than 2 power 2n, because it's a binary function in this expansion. And so, if you take log on both sides again, what do you get? Pi 2n log n minus pi n log n again, but we are not going to write log n there. We would write log n by 2. And we would put the log 2 factor on the right hand side. So that is less than 2n log 2. There was
Minus.
is that minus?
Minus plus.
So here we did a minus. That means here it's coming to be plus, and here to be minus. Minus minus pi n log 2 becomes less. Again, pi n is pi n log 2. Which pi n is smaller than n, but is oh, this is going outside the field. So, this is this and n log 2
Plus.
plus. Okay, let's expand this then. This is log n by 2, that is log n minus log 2.
Yes. And then
then this becomes pi n log 2,
Yes.
which you are adding on this side. So there you should also add 1, right? Plus pi n log 2. And now you could use the fact that pi n is less than n. So this is plus n log 2. Okay. That means you get this is less than 3n log 2.
Okay.
Yes?
Now you telescope.
Yes, exactly. So we use that for telescoping. Indeed. So let x be within this range. So, well, at first let's give this function some name. Otherwise, we have to work with this pi and pi array. So let's define a function of this form pi 2x log x. So let's define the function x by pi 2x log x. Then what we get derivation here that f of 2n minus f of x is f of n minus f of n by 2 that is bounded above by 3n log 2. Right? So now take this n's, put that inside f of 2k minus 2k minus 1 is less than 3 log 2 times 2k and so on. F of 2k minus 1 minus f of 2k minus 2 is less than the same thing here times 2 power k minus 1 and so on. I say f of 4 minus f of 2 is less than the same thing here and here, just 4. Okay. So if you sum this up, what happens? This cancels, and there's lots of cancellation except this minus f2, which will go on the right hand side. Okay. So what we get? F of 2k is less than 3 log 2, and this sum, let's write it down on the board on the right hand side. So if you sum this up, you get f of 2k always above by 3 log 2, and the sum runs from 4 plus 8 plus etc. to power k, and this minus f2 comes on the right hand side. So plus f, when what was f of x was pi 2x times log x. So this will be pi 4 log 2. x is less than 2 to the power 3 log, right? Yeah, 3 log 2 times, you can just take 1 plus 4 plus carbon dioxide. Okay, and that is again less than 3 log 2 to power k plus 1. So f of 2k is less than this one. What was f of 2k? It was pi x log x. So that is pi 2k plus 1 is less than 3 log 2 k plus 1 by log 2 k, right? Well, this doesn't match so nicely, so let's just put 6 there. 6 log 2 times 2k by log 2. Well, now choose x such that let x be larger than 4 and choose k such that 2 power k is less than x less than 2 power k plus 1. So there will be a unique k given x such that this happens, right? We can use that code. So now what we get? Well, note that x is larger than 4, so this k, 2 power k, this is in fact larger than 4. So you are in the range larger than e, and so you can use again the fact that x by log x is an integer function. So you have now pi x. Now we are trying to get a lower bound on this. So pi x is larger, yeah, pi of 2k, and well, for pi of 2k, what do you get? Oh, sorry, we're trying to get a upper bound. Lower bound we have already got from this previous arguments. Pi of x
Less than equal to 2 power k plus 1. Pi.
right. 2 power k plus 1.
And then this is less than 6 log 2.
Right. Times
2 power
k by log 2k.
and then this is increasing.
This is a function. So this is then less than equal to 6 log 2 x by log x. Okay. For all x in this range, x is equal to 4, and then it's rather easy to verify for the x in range between 2 to 4. So that finishes the proof of Schilling's theorem. Now, what were our bounds? Let's recall the bounds we obtained so far is 3 log 2 by 8. This times x by log x is less than pi x less than 6 log 2 x by log x. And as you mentioned, these are not good enough for proving what is postulated, but we will do something, I mean, we'll use the